Hi there, so let's work in the case setup. So let me launch Fluent, and just to remind you again, this is a 3D case, so remember 3D case, you need to enable here this option 3D, and then just choose your resources according to what you have available, okay? So let me put the directory where I have the files, and I think I'm ready to go. Okay, so at this point it's launching Fluent, and we just need to read the files. Okay, so again, I have my solutions. This case is rather economical. Okay, so I will launch. Yeah, let's launch the simulation. It's rather economical case. So okay, actually I need to switch here. Okay, and to okay, just give me a minute. Okay, actually I open in the wrong directory, so let me close. Let me launch again. So I have my answers student here. Okay, so I should launch it here. So 3D, sure that this is the right directory. So you have the cases here there. Okay, so let's launch this one. The case setup is straightforward. Then I will have also my Fluent solutions. Okay, I have different models, but this is very economical. Shouldn't be a problem to run. Okay, so let's open case data and Fluent cases. Let me open this. And as usual, okay, we have the case read, we read it, and let's explore the mesh. Okay, so see that this is what we have. We have an inlet, outlet, and then those walls. And it's into this what is happening. The flow entering here, and then you will have the vortex there produced. So basically, let's go through the case setup again, okay? So this is very standard. Again, we're running steady. Then in tutorial 14, we're going to focus into scale resolving now and less and that stuff. Even we're going to show you a DNA. So we switch here for transient, but the idea is pretty much the same. In transient, we only need to solve for time now. So you need to choose the time step. We already work it out in one tutorial. So choose the model, okay? And here you choose any of the eddy viscosity, okay? Or even Reynolds stresses, and you can compare the solution. So let me choose here K omega st. See that you have the production limiter because by default it's enabled, but again, if you switch to another model, well, again, see that it's enabled by default, but it's actually a good idea because here you're expecting a large stagnation area. So it is a good idea to enable that one. Disable the curvature correction. Okay, we're not going to run with that one. And the case setup is standard. Okay, so you go to boundary conditions, it's incompressible. So you have an inlet, an outlet, and then you have the other walls, the slit walls. Okay, so setup here, the solver, default values are okay for the moment. Set up your monitor. So see here we have Y plus, I think it's average, yes. I know it's facet maximum, so let's put it facet average is the one that we should compute. Okay, so see that actually it's a wall resolving mesh, and we have the different forces and imbalance there. So we can go initialize and let's launch the simulation. Okay, you already have a solution there. Okay, but let's launch, because if I will recall this case, it's very economical. Okay, so we can see everything, how it's evolving, okay, in real time. So see that we have the Y plus, so we have two walls. Okay, if we have the bottom and top wall, each one will have obviously can have different Y plus. So this is the values that we have. We have the drag and leaf and lateral force. It is computed on the vein, okay, just in the vein, not in the ground. And this is the imbalance, okay. So you have what is inlet, what is entering, and outlet, what is going out. So as you do the summation, you should get value close to 0. And these are our residuals, okay? So remember, K omega is still without curvature corrections. So we shouldn't get a good resolution of this vortex that you see here, okay? So the Reynolds stress is just capturing very nicely. This one is failing, okay? So let's see what happens. So as you see, the residuals, they go down quite fast, okay? So let's wait a little bit. If I will recall, the convergence criterion is 10 to the minus 4. So don't recall well, so let's wait a little bit and see what happens. Okay, this is 10 to the minus 3. We have a solution. Okay, always remember this is not your actual solution. You should monitor integral quantity, so see that the CD is okay and the lateral is okay. Probably we should let it run a little bit because this one seems that this is still oscillating a little bit, but let's take it for granted. This is a good solution. Again, we can visualize. So remember that now to visualize those vortices, we can use isosurfaces. Okay, so first, okay, let me go here and I created 2 planes. I'll see here that you can plot velocity, stuff like that, or you can plot bottom and vane. See that we plot here pressure contours. Okay, the interesting is that we want to capture that vortex. See that we have it here, but to capture that vortex you need to use isosurfaces, so surfaces with the same value. So you generate that here, isosurface, and to capture this, you can use Q criterion or lambda 2, that is specifically formulated now to capture that vortices. So you have it here under velocity. You should have here Q criterion normalized, Q criterion rho, and lambda 2 criterion. I like to use the Q criterion rho. Okay, let's use this one. Select domain, and then you can create. And then that after you create it, you just play with the values, okay? So the thing is that to capture the vortex, the Q criterion is a positive value, okay? So sometimes it's tricky to find the right value. So usually I start with something like 1000 and then I just start to adjust that value, okay? So let's see that 1000 and getting this, okay? So it's capturing too many structures, okay? So let me go put it like this, okay? So let me recall what I put here, 50,000. Okay, so let's go 50,000. So see that also that what you see depends on the value that you put, okay? So probably 50,000 is too high, so that's why. No, but again, it's a good indication because all these cases, they have the same value, 50,000, okay? So see, this is what we have, okay? This is what capture. So now let's rerun, not rerun, keep running, but enable this curvature. And if I go here and then press calculate, launch, okay, you have the jump there in the residuals. And now let's see what happened with the behavior. Okay, so it converge, everything is stable, nothing is strange. So we're happy, and now we go back here and see that we're plotting exactly the same isosurface and see that now we capture more structures. So this is the idea, and this example, okay, you see clearly the influence of that curvature correction. I want to add that also that curvature correction can be added with geometrical curvature, like in the first case. So for instance, in airfoils, this will find the situation towards the tips of the wings, in 3D wings. So remember that the surface is curved, so also this one can add some dependence in the strain rates, okay, and in the spin tensor. So it is desirable also to add this curvature correction, okay, if you want to resolve very well this vortex core, okay. So this in wings, in airplanes, you will find it in the tips, okay, in the wing tips. So let's run again, okay, so we keep it there, and let's switch now. So we know that the same stuff will be, so see that the K omega, now we go to the parallel matters, leave it enable. Okay, so this parallel math should give much better results than these ones. Okay, we saw it in the slide. So see that nothing changed. Okay, that curvature correction is, and I didn't point out something though. Let me go here. Okay, so let's finish this simulation, and then just to point out something, that this parallel math also, it has different formulations. Okay, and those formulations can take into account also some curvature vorticity of the system, just to improve this kind of applications that you have these winded vortices. Okay, so let me stop it here just to make it, to show you. So see that here you have different formulations. Okay, vorticity based, extreme vorticity based. So in theory this should be better. Okay, just because you are taking into account more information. Okay, but that is in theory, not necessarily in practice. Okay, so let me change here and let's see what happens. But this is the concept. Okay, so let's see, let's wait until we reach the final tolerance. Okay, so we reach final tolerance, and again, let's go here, and I just want to plot this one and see that we have a nicer vortex there. Okay, remember, using the same criterion, and you can compare all the methods, K omega, K epsilon, you will see that this one, it captures better this vortex here. Okay, also you should quantify. You will see that your CD, CL, they are similar in all cases. You see here, you have here the whole evolution, so you see that there are not big changes. Okay, but again, this is something that you should quantify. And finally, okay, just to illustrate, remember also you can adjust this coefficient. So usually 1 is okay, probably you can increase it a little bit more, but it's quite difficult now to give you a guideline how high it can be. But I don't go as high as 4 or 5. I don't go, but again, it's a trial and error kind of. So just to show you again, as you go here, Reynolds stress, now these models, those corrections are disabled. You need it. They're fully anisotropic models, and it's up to you to run. So if I go here, linear pressure strength, this one is very difficult to make converge. Let me enable this one, and let's see what happens with this model. So it's very difficult to make conversion. See that you have that high jump. Even if you have a good initial condition, you have this high jump, and then you need to let the solution go in time until it settles. Hopefully, crossing fingers, it won't converge, but don't be surprised that they converge. But that is in particular this formulation. Okay, and see that now it's going up. Okay, so see that this is just now an indication that it's starting to diverge. Okay, so this is the sense that, as mentioned, that it sometimes can be really difficult to make converge. Okay, so in particular, you will see that behavior with the linear one. So it's better to use the quadratic or the stress omega, any of these two. So the quadratic, let's see what happens. Even if we have this rubbish starting field, let's see if it managed to. Okay, so see that it's giving you this very bad warning. See that you have negative Reynolds stress. So you are not fulfilling the realizability condition that they must be positive. So at this point, it's failing. So see that this realizability should be enforced. It's not enforced in this model. So when you look at the K omega realizable, you have that realizability condition that those Reynolds stresses, they need to be always positive. Okay, so let's start from scratch and see what happens. Okay, let me initialize. Okay, and go ahead. So I'm using this second order strain. Okay, and hopefully this one is going to work. Okay, so this is the things that I was mentioned, that they can be very tricky to make converge. Sometimes they converge if you start from uniform solutions. Sometimes you need to start from a fully converged solution, and sometimes it doesn't matter how it starts, it will always diverge. Okay, strongly depends on the values that you are giving out or the discretization. Okay, so in this case, since that it is working. So I will let it run a little bit more. Okay, so see that everything seems to be stable, balanced. So I will let it run for a little bit and let's see what happens. Okay, so the solver is running and see what is giving this funny message that is telling you that you have negative and now it's diverging. So you see that now again this one is still, it is diverging. It's not very easy to make conversion. I would like to have one of these converging. So let me initialize again and let's use, usually this one and this one also, they work relatively well. Okay, so this is the model Reynolds stress based in the omega equation. These two are based in the epsilon equation. So this one hopefully will work fine. Usually my personal experience is the one that works. Okay, so now again I will launch and let's wait a little bit. Okay, so in my case, it converts about 92 iterations. So as I say that usually the omega formulation tends to have better convergence properties. See that everything is smooth, no funny messages that about having negative normal Reynolds stresses. Remember that those by definition should be positive because it's the fluctuation square, so there is no way that it becomes negative, but numerically speaking it might happen, and it was happening in the previous cases. In this case everything was smooth, and again we can go here and see that you plot and then you capture this. Okay, so see that you have this one, the horseshoe vortex here, another vortex here. Okay, you have all your vertical structures. Okay, and again you can get the other velocity. So see here that the vortex core, you have it there. Okay, and we can go and plot there the turbulent viscosity and see that the idea is that the core shouldn't produce too much viscosity there. So as you see there, that is the behavior that we have in this case. So a nice case, as I say, no validation data, but we understand well the physics. Okay, so I think that is all for these corrections, the production and curvature correction, and I think it's all okay for all the range models. So in the next videos we're going to move to SRS, less simulations, and probably show you also DNS. Also the next tutorial 13 will be in your own, so I will just introduce you the case and it will be up to you to set up that case. So that's all. Thank you very much for the attention. See you next time. Bye.